In the last lecture, we discussed circular motion and some problems associated with circular motion. You would recall that when a body moves in a circular orbit, it experiences a force towards the center of the circle called centripetal force. Today, we take up another important topic, collisions between particles. Collisions may be thought of as an application of the conservation of linear momentum. So, let us start with the definition of a collision. What is a collision? A collision is an event in which two or more bodies interact for a very short time and exchange energy and momentum. The event could be such that the two bodies actually collide, they come and collide with one another, or they could interact at a distance. Two balls shown here have collided such that they are touching one another. A collision between a truck and a car is also such that these two bodies come into contact with one another. However, there are collisions like the collision between a proton and an electron, in which the particles do not touch one another, they interact from a distance, they interact through a field. In this case, in the case of electron proton, through the electromagnetic field. They could also interact through gravitational field, and one important example of this kind of interaction is the slingshot effect. You have heard that the missiles or satellites launched from the earth are guided to another planet, so that they pass around that planet at a very short distance and gain energy. This is shown in this sketch. A satellite is launched from the earth, it passes around Venus, a very short distance from Venus, and in doing that it gains energy, so that it can continue on its path. If a system is isolated, the two particles have certain momentum before collisions and the same momentum they have after collision. In this case, you can see these two bogies of a train, they have momenta mv1 and m2v2 before collision, and after collision, if the two join together, then their momentum is m1 plus m2 times v, where v is their common velocity. The idea is that the momentum before the collision is equal to the momentum after collision. In this special case, you can consider collision between particles which stick together, that is, they collide and then they stick and then move as one particle, and for them you can see the equations are such that the final velocity of the two particles is the same, and therefore, we can, from the conservation of momentum, we can find that this final velocity is equal to m1 times the initial velocity of particle 1, m2 times the initial velocity of particle 2 divided by the total mass of these two particles. If the second particle, which we always call as target, is initially at rest, then v2 is 0, and then Vf, the final velocity of the two sticking particles, is m1 v1 initial divided by m1 plus m2. And if m1 is equal to m2, you can easily see that the final velocity is half the initial velocity of particle 1. This is sketched here. We have particle 1 shown by this blue dot. This has velocity vi1, and then vi2 is the target. This has velocity 0, and after the collision they stick together and they move with velocity Vf, which is vi1 divided by v2. Collisions are two types: elastic collisions, in which momentum and kinetic energy are conserved, and inelastic collisions, in which momentum and total energy of the participating particles are conserved. Once again, elastic collisions, in which momentum and kinetic energy is conserved, inelastic collisions, in which total energy and momentum are conserved. Collisions between hard steel balls are very nearly elastic. Steel is very elastic material. Therefore, if we have steel balls and if they collide, then those collisions are more or less elastic. Collisions between particles of a gas, ideal gas, they are thought to be totally elastic, so that one can calculate the pressure, etc. Here I have given example of an elastic collision and an inelastic collision. And if I throw a ball, it collides with the floor and then it bounces back. If it bounces back by the same distance, exactly the same distance, then we say that the collision is elastic. If it does not, as shown here, and its amplitude goes on decreasing as it bounces back, then we say that the collision is inelastic. In this lecture, we shall deal only with elastic collisions, because inelastic collisions are very difficult to deal with. So, what we have is, in the top row we have two particles which are coming together, they collide as shown here, and then they move back and move away from each other with the velocities with which they came. If the collision is elastic, then they would move back with the velocities with which they approached each other. Let us go a little deeper into the physics of collisions. What happens really? Let us see. We have two balls once again moving towards each other. When they collide, they actually suffer some deformation in their shapes, as shown here. They are slightly deformed, and when they are deformed, the energy of deformation is stored inside these balls as potential energy, and after a short while this potential energy is recovered as kinetic energy, and the two balls then move away from each other. The important thing to remember is that all the potential energy is recovered as kinetic energy. There is no loss of energy as heat, sound, or any other form of energy. I give you another example. You must have seen this trick played in many fairs which are organized in villages and elsewhere. Here is an athlete who is ready to jump on a rope which is elastic. In the second one, he has jumped on that rope, and the rope, you can see, has suffered some deformation. This deformation now becomes the potential energy of this rope, and very soon it recovers its shape, and the potential energy is given as kinetic energy of the athlete, and the athlete bounces back to the same height. If the collision is perfectly elastic, then the athlete must bounce back to the same height. Let us now do some mathematics. Elastic collision between two particles. Conservation momentum is given by P1I plus P2I equal to P1F plus P2F. Remember, all these are vectors. Or M1 V1I plus M2 V2I equal to M1 V1F plus M2 V2F, and we are assuming that the velocity of particles is much smaller than the velocity of light. And conservation of kinetic energy, M1 V1I square plus M2 V2I square equal to M1 V1F square plus M2 V2F square. These are our guiding equations and or conditions, and both these conditions must be satisfied in a collision which is elastic. So, from these two equations we can solve them. It is easy, you can always do that, and we get these expressions for the final velocities V1F, V2F. Remember, in these two equations there are two unknowns. Those are the final velocities V1F and V2F, and we have got now the expressions for these. Remember also that we are now doing collisions in one dimension, so that there is no need now to distinguish between velocity and speed. So, we are using magnitudes rather than vectors. So, these are the expressions for V1F, V2F. If the target particle is at rest, remember what is the target particle? Target particle is the particle on which the colliding particle is incident. Second particle is at rest, the first particle is incident on that target. So, if the target particle is at rest, that is V2I is equal to 0, then this equation V1F becomes very simple. and V2F is also very simple, and we can now study special cases. The first case is when the two masses are equal. I mean, two balls which are colliding have equal masses. What happens then? I have sketched here before and after. This V1I moving this way, V2I is equal to 0. We will see that V1F becomes 0 and V2F becomes V1I. We shall see that in a moment. And here is something that you can see in many science parks. For example, in the NCERT science park, you can see this machine called Newton's cradle. It consists of odd number of pendulums, and this shows the conservation of momentum in a collision. You take one of the pendulums as slightly and then let it fall back on the others, and you will see the end pendulum goes off by the same amount as the amount by which the first pendulum. So, this sort of is a confirmation of what we are doing. So, we saw that in a collision between two particles of equal mass, the incident particle transfers all its kinetic energy to the target particle. Even if the masses of the colliding particles are nearly equal, sharing of energy between the particles during collisions is quite effective. This is the basis of the use of moderators in nuclear reactors. I think be familiar with moderators. Moderators are used in nuclear reactors. Why? I shall tell you in a moment. What we have to remember is that if two particles have the same mass and if they collide and the collision is elastic, then the energy of the first particle is transferred to the energy of the second particle. That is what you need to remember, and that you can show from the equations that we have derived. Here I show you the sketch of the nuclear fission. We have a neutron which attacks a U-235 nucleus, and there is a breakup of the nucleus into two nuclei, barium and krypton, and there is on an average emission of 3 neutrons. These 3 neutrons are very energetic neutrons. They move with very high velocities, and therefore, the probability with which they can attack another U-235 is small. What we need to do is to slow down these neutrons, and that is where we use the moderator. Moderator, as I have told you already, is some light material. So, the neutrons are made to collide with the molecules of this light material. They share energy and thereby they get cooled, or their energy gets reduced, their velocity gets reduced, and the probability of their causing another fission reaction increases. That is the role of the moderator, and moderators are usually ordinary water, heavy water, or some graphite. These are all light materials. Case 2. In this case, the mass of the incident particle is much smaller than the mass of the target particle. That is, a light particle is hitting a heavy particle. In this case, again you can use equations and you can get V1F is equal to minus V1I. That is the final velocity of the particle 1 which is coming is in the opposite direction. That is, it collides and goes back with the same velocity with which it came, whereas the velocity of the second particle is very small, it hardly moves. In this collision of a very heavy truck and a car, the car is coming, it collides, and the car moves back with the velocity with which it came, whereas the truck hardly moves. This is when a very light particle collides with a heavy particle. And the case 3 is when a very heavy particle collides with a very light particle. You can see V1F is equal to V1I, that is, the velocity of the incident particles remains intact, whereas the velocity of the second particle, the target particle, is equal to twice the velocity of the incident particle. I will show you the figure here. A truck is hitting a stationary car from behind. The truck is coming with the velocity u, hits the car from behind, and what happens? The truck keeps moving with the same velocity u, whereas the car now moves with double the velocity of the truck, 2u. that means car suffers a great deal of damage when a truck hits it from behind. Now, so far we have taken on head-on collisions. Actually, head-on collisions are, whenever particles collide, they don't always collide head-on. Most of the time the collision is in a plane. So, now let us study elastic collisions in a plane. The particles, as I said, do not always collide head-on. Therefore, the collision is in general in a plane. The plane is defined by the relative velocity of the colliding particles, the direction of the relative velocity, and the direction of the force between particles. The force between particles can be taken as the force along the lines joining their centers. So, these two things, this line and the relative velocity of the particles, that defines a plane in which the collision takes place. As before, we assume that the target particle is at rest, and here is the collision. Before collision, here is a particle, this yellow ball which is coming, the target is at rest. So, the target velocity v2i is equal to 0, and what happens after collision? After collision, you see the yellow particle moving this way and the blue particle moving this way, the yellow ball moving that way, the blue ball moving this way. Both move, and in this collision the momentum is conserved. Therefore, P total momentum on this side is just P1i, because the second particle was at rest, it had 0 momentum. After collision, the momentum becomes P1f plus P2f. The momentum of single particle is now shared by the momentum of two particles. That is the collision in a plane. I will show you what happens. This triangle shows the conservation of momentum. This blue and this black, they are the original momenta, and this red one is the original momentum, and these two are the final momentum. So, we have before collision only single momentum, which is this. After collision, both the particles are moving, therefore, these two particles have momenta which are shown by this, and they form a triangle because of the conservation of momentum. Interesting case is this: if the masses of the two colliding particles are equal, we have a very interesting situation. Suppose the target particle is at rest, then the conservation of momentum and kinetic energy gives these two equations: v1i equal to v1f plus v2f. Because the masses are equal, therefore, they have been removed. The kinetic energy of the first particle is v1i squared, and of the particles after collision v1f square plus v2f square. And just look at the second equation. What does it show? If you remember your Pythagoras theorem, you would see that v1i, v1f and v2f, they form a right angled triangle, as I have shown here. v1i, v1f, v2f, they form a right angled triangle. v1f and v2f, they are at right angles to each other. The final momenta of the two particles, they are at right angles. That is, after collision, when they move at right angle to each other. Let us see. Here again, before collision, we have a particle coming with velocity v1i, v2i is of course 0. The target, remember, is at rest. They collide, and when they collide, the blue one moves in this direction with velocity v1f, and the yellow one moves in this direction, which makes an angle of 90 degrees with this direction, and this has now the velocity v2f, and v1f and v2f, as I have said before, they are at right angles to each other. Look at the triangle. This is one v1f, v1f is this. This is v2f, you can see that they are parallel and have the same length, these lines, and this is the initial v1i, initial momentum, and they form a right angled triangle, and this angle is 90 degrees. If you have seen a billiard table, then you would have seen this phenomenon. You know, all billiard balls, they have equal mass, and since they have equal mass, so whenever a billiard ball collides with another billiard ball, they move at right angles to each other. This initial, the ball which comes and collides with a ball which is stationary, this ball is called a cue in terms of the billiard language, so to say. The players call it cue. So it is a cue. So you must have seen the person doing this, you see, and he keeps on aiming, so that these two balls which move, they move in such a way that they go to their respective homes. And it's very requires a lot of skill, and not only lot of skill, it requires knowledge of collisions also, collisions between particles which have equal mass. So the cue is here and it hits this ball, and you can see that it hits not head on, at an angle, and then the two diverge, one goes this way, the other goes this way. This makes an angle theta 1 with the initial direction, this makes an angle theta 2 with the initial direction, and theta 1 plus theta 2 is equal to 90 degrees. And skilled billiard players, they know all this, and they use this knowledge so that they can aim and send the balls to their respective homes. In the next lecture, we shall consider the topic of center of mass. You remember, center of mass is a very difficult and very important concept, and we shall take various examples and explain in various ways what center of mass means.